So welcome to this satellite session of the March meeting on network dynamics and synchronization. This session is organized by the ICTP-SAIFR in São Paulo, Brazil. My name is Marcos Aguiar. I'll be chairing this session. So I just want to remind you that all microphones are going to be muted during the entire session, and you should submit your questions by using the chat. So if you are watching on YouTube, you can do that as well. I'll be trying to monitor the questions there and pass it to the speakers. First speaker is Tiago Pereira. Tiago is a professor at the Institute for Mathematical Sciences and Computation of the University of São Paulo. Right now he's in Germany, and he's going to be speaking on coherence resonancing in networks. So please, Tiago, you have around 25 minutes. I'll let you know when you are about 2 minutes to end, so you can control your time. Okay, so please go ahead.
Yeah, perfect. Thank you very much for the invitation. It's a pleasure to be here. This is a joint work with Ralph Tonis from Potsdam University and Carlos Fiore from University of São Paulo as well. I will be speaking about synchronization, and I will focus on this particular example most of my talk. So what you see here is a network. You have two hubs in the center of this network, one red hub and one blue hub. And then you have this red group, so the nodes attached to this hub, marked in red. The nodes attached to the blue hub attached in painted in blue. And then you have this community in the middle that I painted green. I will call a node a hub when it has a lot of connections. So from the structural point of view, a node is a hub when it's massively connected, as the center nodes are. Later on the talk, I'll tell you that what I'm going to see and explain this talk holds in very general for more complicated networks, but for now, I'll focus on this network. So this is the structure of the network that I want to describe. So now on what I'm going to do, on the top of each node, I will have a dynamical system. And I'm assuming now that the dynamics on top of each node, if I were to isolate it from the network, is a periodic dynamics. But I'm also assuming that the frequencies, they are different. So each node has its own frequency, and I'll set up parameters in such a way that if I take this model now, couple it through this network, this model does not synchronize. So this is possible to do, so the deterministic system does not synchronize. Yeah. If the deterministic system does not synchronize, the question is, how can we make the system synchronize? This is kind of interesting question because many of the examples we find in real world, they resemble this kind of network. So you have hubs, then you have nodes coupled to the hubs, nodes coupled to the other hubs, and nodes coupled to both hubs. So this is very common structure. And what I'm saying is that when you find this structure, it's very hard to synchronize the system. So this was some kind of apparent paradox in this theory. So if nature is evolving to have this kind of structure, why is it hard to synchronize this kind of structures? Yeah? Why is it hard for this kind of structure to have a network, to have collective motion? So what we did then is to see what's the response of this kind of network to noise. So what I'm going to do now, I will pump noise everywhere. I will pump noise into the poorly connected nodes, the leaves, and I will also put noise to the hubs. My noise, they're all independent. So on the hub, we'll feel a Wiener process. The other hub will feel an independent Wiener process. The leaves will feel another independent Wiener process. So each noise now will be driven stochastically. So the main point and the main finding that we see is that if you pump the correct amount of noise in the hub now, So I'm assuming that noise in the peripheral nodes are very small. And if you keep on pumping noise to the hub, there will be an optimal noise where the system will tip towards coherence. So now collective motion will be prevalent. Keep more and more noise, this collective motion is destroyed. Yeah. So, but when you pump ideal noise, there will be a tendency that the dynamics will adjust. The oscillators, they will tend to a common frequency, and they will lock and they will perform a collective motion. Yeah. And as I said, so if you're too greedy, if you pump too much noise into the hub, then you destroy this effect. So a strong noise destroys this transition to collective dynamics. So this means like there's a transition from asynchrony to synchrony, then losing asynchrony again is a nonlinear effect. Yeah. So this is my my main point. So at optimal noise in the hubs, the noise will synergize with the network structure and will create a collective dynamics at a mean field level, which will generate a collective motion. To start this problem, I can start this problem in a very general way. I can just say that the dynamics of each isolated system has a periodic orbit, and I'm assuming that this periodic orbit is born from a Hopf bifurcation. Under this assumption, you can write a reduced equation for the system, and you can parameterize the whole system in terms of the phase of the periodic orbit. When you do it, you get to equations of this type, where theta I is the phase of the ith oscillator, omega I is the frequency, and everything else that comes now is the coupling. This psi I is the Wiener process now, and di is the strength of the Wiener process. This function g, we can compute off by hand via this reduction technique, which I said that you can reduce the phase. And when you have this periodic orbit very close to Hopf bifurcation, you can prove that this G has this following form, where this C naught that appear here is the shear in the oscillator. So the shear basically means that when I have my oscillator isolated, the frequency depends on the amplitude. If you have oscillator of this type, it cascades this coupling function having this constant offset from 0. And my next assumption now is the coupling strength. So I have this, which is very common in the literature. Now I have this beta, which now depends on K. K is the degree of the node. So I'm normalizing by the total degree. Somehow my internet says that it's nice, but I think you can hear me well. Yes, but this beta only means that the hub, they couple more to the system than the rest. So this beta will be basically a constant function, and mine is a hub, it increases slightly. So this means now I have two effects in the system. A hub can be a topological hub, can be a structural hub, and can have its beta very large. So this means like it will play a dominant role in terms of structure, but also in terms of dynamics. And if a hub also plays a dominant role in terms of the dynamics, then I'll call it influencer. I can take that equation that I just showed and do some massage in this equation to bring it to a-dimensional quantities and so on. When I do this, a very important parameter will pop up, which we call the effective frequency gap in the system, where this effective frequency gap, big omega, will be delta omega, small omega, which is the difference between frequencies of the hub and the leaf. This number can be large, can be 0. It doesn't play a role here. And then there will be some number popping out from the connection between network and dynamics already, which we call the structural gap, which is beta times the C naught. So the beta times the shear. So basically what the shear does after you rescale the model, the shear will play a role of a frequency and will speed up the frequency of the oscillator. This is the main effect of the shear, and that's easier. And in the beginning, I told you that if the noise is optimal, if the noise is not too small or too big, then the system would tip towards synchrony. While too small or too big in this problem is with respect to this effective frequency gap. So what I will do, I will put this parameter now, which will be my main control parameter. This is small q, which the strength of the noise G divided by the frequency gap. So Q1 for me is large, Q much bigger than 1 is very, very large, and Q is small coupling with respect, small noise with respect to the frequency gap. So to tackle this problem, actually to quantify synchronization, what we do, we introduce what we call the order parameter. So basically we see how the phases, they are distributed in the circle. So that will be the idea. So if the phases, they are moving together, they will form a small cloud of points in the circle, and this will make this R be very large. And if these phases, they are uniform distributed, then this R will be very small, so the amplitude of this cloud. So I will do this following idea. So if R is very large, if R very large now means 1, if R is close to 1, I'll say the system is synchronized. And if R is close to 0, I'll say the system is not synchronized. So that will be the main parameter that I'm going to use. So in this example now, what I will do, I will take this network that we presented in the beginning. And each of these communities, the red, the green, and the blue, they will have 300 nodes. And I'll do the simulation. So first for Q is small, so Q is 0.2. I start the system at random initial conditions. I have some dispersion in frequency following a Lorentzian, and then I start the system. I see some oscillations. There's in these plots, in the y-axis, you have R, which is this parameter, which is quantified synchronization. In the x-axis, you have time. So you see it's oscillating around 0.1, which means the system is not synchronized. Then I increase Q to 1. So now I'm in the ideal coupling regime. So you see excursions now to big values of R. So this means the system is synchronizing. And if I push now Q very large, so Q7, the system desynchronizes again. The system is stochastic now, so R will not go to 1, stay 1 all the time. So you can see that R can go very, very large and then can drop and so on. You can say what the distribution of R, what's the expected value of R, and characterize the stochastic process. So this dynamics of R now will be stochastic. Let me show a movie here so we can see what's going on. Let me try to play this movie now. So in the x-axis, you have 900 oscillators. So the x-axis is indexing the oscillator. In the red group, the blue group, and the green group. Green here now is white. And in the y-axis, you have the phases of the oscillator going from 0 to 2 pi. And I'm identifying 0 from 2 pi. So this means like if a node is growing, once it hits 2 pi, it will pop up again in 0. So I have a periodic boundary condition. So the move now is running. And dispersion in this phase is all the way as it started. This not synchronized. As time goes on, you see a tendency that they form packing. So the blue groups now are packing together. So now this problem will have a couple time scales. So first, the groups, they will try to pack together. And once they pack together, some kind of mean field evolution will start, and then the mean fields will interact. So this is the problem we have to understand. So I'm telling you that synchronization will happen in the system over multiple time scales. So first the group synchronizes. Once the group synchronizes, the groups, they will start interacting and try to synchronize between themselves. And this problem is still stochastic. You see that sometimes they come together, they drive together for a while, and then noise will take them apart, and then they will try to synchronize again, and this will go on and on. But on average, this packing will be very tight together. If you keep on running the simulation, you see that eventually they will pack together, and they will have a higher tendency to go together. I will spare you from watching this movie over and over again. Yeah? I think this is okay now. So what I will show to you now will be like the same movie that you just saw over multiple cues. So what I'm going to do now in the in this picture, so let's zoom picture C. This is for picture A, so I have this network, the same style I presented before, where I have 300 nodes in group A, in the red group, 300 nodes in the blue group, and 300 nodes in the green group in the middle. So the picture below, figure C, I'm doing the following. So for each value in the x-axis, I will simulate my system for 1 million time steps. Then I'll record the value of this parameter R. And what you see now is will be the histogram coded in blue. So blue means, like, dark blue means the probability to find R in that value that you see is very high. And as you go to white, the probability is decaying. So what you see here is that if you take Q in figure C, Q very small, then basically means the system is not deterministic, and R is zero. So this is what I told you, that the deterministic system will not synchronize. So, but then you start increasing Q, and for Q near 1, you have a peak. So the system goes to synchronization. This is a purely noisy-driven effect. And then if you continue increasing Q, synchronization will be lost, and the order parameter will drop. This figure C is for this value beta equals 10. Figure D is for beta equals 100. So what you see is like a beta equals to 100 means the hubs play bigger role in the network. When the hubs, they play bigger role in the network, this curve, it drops quicker, and it tips quicker as well. So this means like bigger beta has the effect of squashing the variance along this curve. In the red curve that you see is the theory we developed for beta very large. So this means frequency gaps very, very large. At the end of the day, this is what it means. This effect is very robust. I presented to you for this very particular network where you can prove what we see. But actually, if you do numerics, you see this effect in basically we saw in all networks that have influencers that we checked. For example, I will show you two. The upper layer is a network of political opinions of the US election in 2008. And the lower panel is the network of the C elegans. So we took the hubs, turned the hubs into influencers, and did the simulation. So weak Q here now will be 0.1. So we see in both cases when Q is very small, you don't have a synchronization effect. Q optimal now means Q equals 1. Then the system tips towards synchrony. And Q strong is Q7, the system loses synchrony. So this will be observed through a variety of networks. So with the this is the fact we saw. We are very happy to see this. This solves this this paradox that people had in the past. Why so many networks they evolved to have hubs and to have these groups if they do not synchronize, and synchronization we know is important for the systems. But these networks they are optimal with respect to response to stochastic fluctuation. What I wanted to do now is to explain this coherence resonance effect. So this curve we call coherence resonance, right? So when you pass through peaking coherence, I will try to explain this effect now for a single star, and we can do the theory. Once you understand the single star, you can glue multiple stars. The problem is more complicated, but the key ideas are the same. And so what I do now, I write the equations for the single star again. Psi now will be the phase of this hub, and I raise of the hub. So the first thing to do when you get to this problem is to massage this. So you don't really see the original variables that were given. I will consider phase difference to the hub. So I parameterize I take every phase and see with respect to the hub. If you do this and you write these equations, you can bring this relative phase to this form. And in this form, it doesn't look very obvious, but you can massage this equation now such that it becomes a Riccati equation in the complex plane. And once you have this equation in the complex plane, what will happen is that Riccati equations in the complex plane, they have a symmetry group, which is the Mobius group. So although my system will be very high dimensional now, the system will evolve according to the action of a given group. So which is in this particular case, this group. So this means instead of looking at the equations of the phases, you can just look at the equations of the parameters of the group. So, and this is a three-dimensional group. You have a three-dimensional system of equation to analyze, and then you can understand the whole system. You have to do now some mathematics, prove things here and there, but this is the key idea. So this system can be understood, and you can prove things for it because the system is kind of it comes with a group. So when it comes with a group, it becomes algebra, and then you can just solve it. You still need some kind of averaging theory, but you can do it. But I don't want to bother with the details. I want to give you one idea why we can see this effect. So my argument now will not be sharp. It's not super correct, but it will give you the flavor why you should expect passage through resonance. So let me tell the following. So my oscillators now, the leaves, they each has their own frequency. And I'll assume that they are totally incoherent. Yeah. So they do not synchronize. They're all over the place, very incoherent. If this is true, because the hubs, they interact with the mean value of the leaves, and the leaves are incoherent, they will basically decouple from the network, right? So basically the hubs, they will just become a Wiener process in the circle, no network effect whatsoever. Okay, so now I have this Wiener process in the circle. So this basically means like now the hub became this stochastic driving force to the leaves. And you can now take, under assumption, you can take the equation of the leaves and expand the system. And then you get this sinusoidal driving, right? No linear driving of this Wiener process. This is stochastic driving. So what we do, we compute the correlation function for this process. So I introduce this stochastic process and compute the correlation function. So what we know from the theory is that the effective diffusion of the process is the integral of the correlation function. So if you do the calculation now, you get to this formula. So you see, if the noise in the hub becomes too big, the effective diffusion that the leaf feels goes to zero. So the leaf also decouples. Yeah, so this is some kind of nonlinear transformation through the network. This cannot be the explanation of the process because I'm assuming that I have no synchronization when I did this, and I wanted to explain the peak. But explaining the peak now would involve doing this Mobius action. But this argument shows that right in the incoherent state, you should see some kind of passage through peaks, right, and through resonances. Yeah. So pumping more noise would just destroy the effect. The full description, as I said, so you have to do some kind of mean field theory, which you can do in this model because it comes with the group. So what I wanted to say is that in this particular networks, noise can synergize with the structure and create new phenomena. Yeah, and in this particular case was a transition to coherence that you do not have in deterministic systems. So thank you very much.
Okay, so thank you very much, Tiago. Very, very nice talk. Very interesting. So, so right now we don't have any questions on YouTube. I'm going to start with the questions if people can also ask questions after me. So, so if you do this dynamics in a regular network, in a very homogeneous network, so you expect that nothing is going to happen. The hubs are
you don't see this effect, no.
Okay, and for instance, for the C elegans that you tried, so you run this dynamics on the C elegans, and the C elegans, it's heterogeneous, but it's not strongly heterogeneous, or is it?
This is correct. Yeah. So, but you have nodes that they're more connected. There's a gap in connectivity, right? So
okay, and that's enough for creating this effect.
Yeah.
Okay.
But basically, the effect is like you need some nodes where you pump noise into this node. This node will, the way I see is like you have a node, you pump noise into this node because noises are all independent. But this node will be able to send common noise to quite a bit of hubs, quite a bit of nodes, right?
Yeah. Okay. Although you pump noise into every node, right? But the hub has this special role in spreading
Yeah.
Okay, effectively. Okay. Any questions from people here in the Zoom? I don't see any questions so far in the YouTube.
I have a question, if I can.
Sure.
Sure. Tiago, have you tried to compute the linear stability of the nodes, even uncoupled?
Linear stability?
Yes, to know if the local dynamics, uncoupled local dynamics is stable or unstable to perturbation.
Well, I'm assuming I can do this. I'm assuming that when the system is deterministic, the incoherent state is stable.
Right.
Yeah.
Okay, so okay, so I think we are right on time. So thank you very much, Tiago, for the talk. So now I think we can move on to the next speaker. That's Marcelo Ramírez. Marcelo is our professor of physics at the Instituto de Investigaciones Físicas in La Paz, Bolivia. So Marcelo, thank you very much for accepting our invitation. Marcelo will be talking about Firefly behavior and its dynamical richness from synchronization to oscillation depth. So please, you can go on and share your screen. Again, when you are 2 minutes to 25, I'll let you know. I'll give you a sign.
Okay. Okay, can you see my screen?
Yes, please go
Perfect.
ahead.
Okay. Okay, good evening, everybody. Now I am currently in Belgium, so it's midnight for me. So I will talk about the Firefly behavior and all its dynamical richness. I will focus on synchronization and an interesting phenomenon that is the response to synchronization. As Marcus stated, I work in Bolivia, and for the moment I am in Belgium, and I'm very happy, and I thank the organizer of this satellite meeting for inviting me. Okay, so let's start. This is a picture of my city, a photo of my city. You can see an iconic mountain that is called Illimani. So why I show this picture? It's a nice picture. It reflects the beauty of my city that I hope you can visit in some time. But what is interesting is that we don't have fireflies in La Paz. But happily, we can model and we can construct some electronic devices for mimicking the behavior of these insects. So let's start. This is the outline of my talk. I will give a brief introduction about synchronization and fireflies. I will talk briefly about some qualitative models trying to explain the Firefly synchronization, and then I will focus on our model that is based on some electronic devices that we call it light-controlled oscillators or also electronic fireflies. And then I will describe the synchronization that we found on these oscillators, and also the phenomenon of oscillation death. And finally, I will talk about a response to synchronization that in fact closes the mating behavior in these insects, because there are an interaction between males and females. Okay, let's start. As everybody knows, synchronization is basically defined as an adjustment of rhythms of oscillators due to their weak interaction. And we can consider that synchronization in a certain way is a manifestation of the self-organization in this type of systems. So the first time that the synchronization has been described was by Christian Huygens in the 17th century. Even though it's an old phenomenon, nowadays there are still people working with such kind of oscillators, such kind of pendula, like the work presented by Oliveira and Melo in 2015 in publishing scientific reports that basically they reproduce and explain in a formal way the observations of Huygens. So I will start the firefly behavior asking a question, if you can talk of evolution, of the evolution, because I will consider that sexual selection or mating and synchronization are closely related, but this is the effect of, from a biological viewpoint, of the evolution of the role of flashing behavior in fireflies, that at the beginning they have the role to be an aposematic signal. It means that reject the predators, and then in some species this flashing behavior evolved to synchronization of such flashes, that constitutes a sexual signal that allows some firefly species to recognize their conspecifics. In terms of ways of thinking, this phenomenon has been reported in the 17th century, but until 1920, most of the scientists didn't accept this phenomenon of synchronization on fireflies, and they thought that it was just an illusion, a subjective phenomenon, or an accidental phenomenon. But nowadays we know that the emergence of synchronization on fireflies are real, and it's one of the paradigmatic examples on synchronization. Okay. Let's talk about some simple models to describe synchronization on fireflies. We can start by agent-based models, in which we can we have very simple rules of interaction, and we can choose several strategies of phase delay or phase advance, like in these two cases. And we can see that after a relative short time, the population of fireflies arrived to synchronize independently of the strategy, of the adopted strategy, to achieve complete synchronization. Other models, as Tiago explained it in his talk, are based on phase models. So we have some examples like the Winfrey model, the Kuramoto model, or the Ermentrout model that are very similar, in which the main aspects are the phases and the natural frequencies of the oscillators. Now I will talk about the Mirolo and Strogan model that we call the integrated fire oscillator, or IFO. That is a very simple model consisting of very simple differential equations where we have a dynamical variable V. Each oscillator has its own dynamical variable, and the model is very simple. There is a charging stage until the oscillator achieves a threshold, and then instantaneously resets to the baseline. So with this mechanism, the oscillators can quickly achieve synchronization, as we can see in this plot, where the green dots represent the flashing or the instantaneous resetting of the oscillators. So at the beginning, there's a disordered distribution of such points, of such dots, and finally, in a very short time, there is an manifested complete synchronization. So now I will talk about our model. As I told you, we construct some electronic devices, very cheap, very accessible, with constituting by a flip-flop that is the heart of the oscillator. It's very common in electronics to work with this flip-flop LM555. We worked with some resistors, some capacitors, and of course, in order to ensure the interaction of these oscillators, we work with photodiodes and infrared LEDs. So this is a view of an LCO, an electronic firefly. So we have the LEDs, the photodiodes, the diodes, the photosensors, and we study configuration like this in order to experimentally study synchronization. So what we observe for each oscillator in the oscilloscope, as you can see, are very the signals are very close to the integrated fire oscillators proposed by Miroglio and Strogatz, but with the difference that the discharging is not instantaneous. It's very short compared to the charging stage, but not instantaneous. So we work with the values of the electronic components in order to have typical periods of real fireflies. And then we can see in these films, in these videos, how the system behaves when the oscillators are uncoupled. We don't have any synchronization. On the contrary, when the oscillators are coupled, the system achieves complete synchronization. So in order to construct a model, we will take into account a binary variable epsilon that we showed before. Here during the charging stage, the epsilon, the binary variable epsilon takes the value 1, and during the discharging stage takes the value 0. So for constructing the model, we use the equations related to the charge and to the discharge. We use the natural periods of the oscillators in terms of the electronic components. We impose the thresholds, an upper and a lower threshold, and we introduce the coupling strength by the factor beta Ig that in a certain way, together with the factor delta Ij, can give us the idea of a network. So finally, we have the dynamical systems of the N oscillators with the charging, discharging stages, and the coupling, the coupling term. So in order to represent the synchronization of these oscillators, again, we have the case of identical and non-identical. For the case of identical oscillators, in our polar diagram, we have that the radial coordinate represents the period of the oscillators, and the angular coordinate represents the phase difference. So for the case of identical oscillators, we obtain a complete synchronization. And for a case of non-identical oscillators, what we observe is the cluster formation, but we cannot achieve, at least for a long transient, we cannot observe a complete synchronization. Okay, and to finish with the interesting dynamical behavior, I will describe the oscillation depth that is due to a very strong coupling between the oscillators. We can observe here what it happens when the coupling strength increases. So we see that the signals start to be deformed. Here we lost the periodic oscillatory behavior, and here the amplitude of the oscillation decreases with the coupling strength. And finally, when we have very strong coupling, we have the phenomenon of oscillation depth that coincides with what some inhabitants of the tropical region tell us about what happens when they put many fireflies in a jar. They told us that they observed that the fireflies keep lighting. So in fact, this is the representation of oscillation depth that is reported by inhabitants of the warm regions in Bolivia. So let's talk now about the response to synchronization. So this work starts with a paper published in Science, reports some measures of the female response to virtual males in the space Photinus carolinus. Here we have the male-like flash pattern. In fact, they work with some LEDs as well that play the role of the males. And so they work with 4 situations. The first situation is in which all the males are very ordered signals that could be associated to synchronization. Here we have some a bit disorder, and in the situation C and D, we have completely disordered signals of the males. So what they measure is the female response. So for the case A and B, the female responds very well, more than 80% for the case A, of the order of 70% for the case B, and the response plummets to 10% or less for the disordered cases. So with this, we decided to adapt our model in order to explain this response to synchronization and try to reproduce the results observed by Moiseev and Copeland. For that, we work with the typical male flash pattern of the Photinus carolinus. We have a cycle or a phrase of 10 seconds. We have the intraburst period consisting of the time of the sum of the charging time and the discharging time. We also have the active phase that are characterized by the intraburst period times the number of flashing or bursts. We have in this case 6 flashes for this species. Of course, we can work with other number of flashes as it occurs in other Firefly species. And finally, we have to take into account the silent or quiescent period. And eventually, we can work with a phase delay that plays the role of an initial condition. So this is the same for the male. We associate a bursting oscillator to the males and a non-bursting oscillator to the female. So the dynamics is very different between the males and females. And we will see that the interaction between this kind of oscillators will lead us to observe synchronization on the males and the response to synchronization of the females. So this is the modification of our model, the adaptation of our model. Basically, it's the same model that I presented before, with the exception that we must introduce the silent period, the silent time, and also a condition on the binary variable in order to describe this quiescent period. So we have the quiescent period in terms of the active phase, in terms of the initial condition, in terms of the number of flashes. And finally, we obtain a very similar equation, but with this factor theta I, that we call theta because it looks like to the factor theta that we found in statistical mechanics in order to distinguish bosons of fermions. But in our case, theta +1 describe the bursting oscillators, and theta = -1 describes the non-bursting oscillators. So the dynamical is very different in both oscillators. When external stimuli acts on the charging stage or the discharging stage, for the males, we can see that an external stimulus have an excitatory role on the charge for the males and an inhibitory role on the females. On the contrary, the external stimuli have an inhibitory effect on the discharging of the males and an excitatory effect on the discharging of the females. So what we obtained performing the numerical integration of our equations under the condition in which Moiseev and Copeland worked. So we obtained that the response of the females for the situations A and B are similar, more than 80%, more or less the same as in the case of the measures of Moiseev and Copeland. And for the disordered signals of the males, we have a very low response of the females, less than 10%. So this, in a certain way, this validates our model. And then we worked with some other situations that we can find in nature. So this is the same case, 8 males and 1 female, but here we don't work with a virtual male. We work with a real male, with real males that can synchronize, and just before to attain complete synchronization, the female respond in such a way that the female anticipate the synchronization of males. So here we have the response of the females, the signals of the males. And we can, thank you, Marcus. And we can see that we can talk about the synchronization response. So it works like in such a way that the males synchronize, always synchronize. The females cannot synchronize at all if they are alone. But when we mix the populations of males and females, we see that the males synchronize, and finally the females respond following certain patterns. Here's there's a small video that shows this idea. We have at the center of the video a female. We have the males that have their own synchronous flashing pattern, 6 flashes and then followed by a silence. So we observe that the males start to synchronize, to form clusters of synchronous fireflies. And then just before to achieve complete synchronization, the female respond, emitting a flash. So basically, this is the phenomenon of response to synchronization. We can see that it works for any number of males or females. As we can see here, normally the males synchronize. The females cannot synchronize, but they can respond in a simultaneous way or following some ordered patterns to the synchronization of males, as we can see in the other figures. And just to summarize, I want to say that this is a review of the Firefly synchronous behavior and the modeling of such behavior. We have a huge richness of dynamical behavior. And what is interesting is that we unravel the mechanism leading to the response to synchronization, and one extension of the concept of response to synchronization may be applied to social systems in which the not working with fireflies, but working with some opinions, we can observe or we can describe phenomena such as the consensus or the polarization in some systems of individuals that can respond to synchronization. All this work, if you want further details, are summarized in these two book chapters. Fireflies are paradigm in synchronization and modeling firefly synchronization. Least I would like to mention the Firefly Collaboration Network, Jean-Louis de Neubourg, and in Belgium, Gabriela Conde, nowadays in Imper, Brazil, Nicolas Rubido, nowadays in Aberdeen, Arturo Marti and Cecilia Cabeza in Uruguay, and Jürgen Kurz and Niels Wessel in Germany, and Stephanie de Picter in Belgium. So thanks for your attention.
Okay, thank you very much, Marcelo. We have some time for questions. I still don't see anything coming from YouTube watchers. So if you guys here want to ask some questions, please feel free to do so. I can always start with a question. First of all, very, very interesting. I'm not sure you've seen this, but there is a recent paper. I don't remember the name of the authors right now, but they made some experimental work on fireflies, on real fireflies, and they say that this idea that fireflies have this periodic flashing is actually not true. That fireflies, they flash randomly when isolated, and then when they get together, they synchronize. But these models with the Turamoto models with this periodic flashing is not quite realistic. Have you heard of this? Have you have any comments on that? Yeah. Okay.
Yes, actually, yeah, the Orit Pelex group is working very hard on experimental measures with high tech. And of course, when you perform measurements in nature, first of all, you have the influence of several sources of noise. Mm-hmm. So it's not a perfect synchronization as we can invoke in these simple models, but the idea, the main aspects, the main features of synchronization, such as the response of synchronizations, are real, are not just a random response, because we can also perform or carry out experiments in lab conditions, and here in these conditions are easier to highlight such kind of synchronous behavior and the response to such synchronous behavior of the males. But of course, the work of Orit Pelix group is very interesting, and there are some other models. I refer to Ermentrout model. Now he presented a model, a stochastic model, that in a certain way they try to reproduce the results observed by Orit Pelix group.
Okay, good. Okay,
so there is an continuous evolution of this modeling as well, and the experimental measurements.
Okay, thank you, Marcelo. Well, I think we are out of time, so thanks again very much for your talk. I think we need to move on to the next speaker. Okay, so our next speaker is Sergio Lopes. Sergio is a physicist from the Federal University of Paraná in Curitiba. And so Sergio, thank you very much for accepting our invitation. And Sergio is going to talk about the role of local dynamics in phase synchronization process in network. So please go ahead.
Okay, thank you, Marcos. Are you hearing me? Okay.
Yes. It's all
okay, thank you for the invitation. Let's just me find my presentation here too, because I cannot see both together.
Your presentation is not in the presentation mode. We can see the slide of our slides, but it's okay. Oh yeah, that's better. Okay.
Yeah, now I think it's now better. Yeah.
Yeah.
Okay, thank you, Marcos. So my name is Sergio Lopes. I'm from University of Curitiba, Paraná. I'm going to talk today about the role of local dynamics in phase synchronization of network applied to neural network, in fact. It's a collaborative work with Emanuel Cambraia, Tiago de Lima Prado, and also João Vieira Flauzino. All of them work together with me here in Curitiba in the same physics department. I'm give an outline of my talk, just a summary, and say something about the background of synchronization, and give you also some flashes about the importance of the synchronized behavior in a brain, in a neural network. After that, I will talk about the neural model I use. It's a mathematical neural model to simulate the behavior in the collective behavior of the network, and followed by results and conclusions. So let's start with some background of synchronization. The sync phenomena is just the action of a lot of neurons working together, and the individual dynamics of the neuron give place to what we call collective behavior or collective enrichment behavior. Sometimes we say that the enrichment behavior occurs in chaos dynamics or even regular dynamics. And the coupling is imposed by the collective dynamic is imposed by the coupling, but also they occurs due to the local environment of the neurons, what we call here the local dynamics. And the collective dynamics is not just a sum of individual dynamics. In fact, it's a new dynamics, exhibits its own features. So the synchronization behavior is a change from the local dynamics that can be chaotic or regular to a collective dynamics. And what is important to synchronize neurons? Well, the cooperation of neurons is fundamental to understand the complex behavior of the brain, because if you see an apple, the apple is just a sum of impulse that some part of the neurons related to the vision, for example, they react about this input and say to you that those images are apple. So you see, you feel is a collective dynamics of some parts of the brain. And it's related to the level of correlation among the neurons. Yeah, the cooperation of neurons imply in some correlation of phase about them. And many topics have been considered to construct coupled network, and based in experimental evidence, we can find in nature small world networks. We can also find global network, scale-free networks, and in the brain, there is a lot of works that say that some parts of the brain is just a random network. Some part of them is small word network. Here I use a small word network to show because I don't have too much time to show more examples. And the correlation of phase occurs when the neuron starts and sees its activation almost in similar time. Yeah, we don't have complete synchronization in brain. We just have partial synchronization of phase of the neurons. Yeah, the level of synchronization so is related to the coupling, yeah, and the effect of the local dynamics. The local dynamics can be chaotic or regular. So if you choose a model for your neurons that present both kind of dynamics, will be dependent on the parameter. So I will show you that that's very important to understand the synchronization behavior of the entire network. And the network of the dynamic of the network will be function of local parameters. I think the main parameters for a neuron is the ion channel conductance. Well, how this ion channel operates ions from outside to inside the neurons. And about the importance of the synchronization, experimental evidence show that the neuron dynamics is more related to the individual parameter of the neurons than to the coupling itself. Yeah, experimental setup show that sometimes you can see lack of synchronization, excess of synchronization, and this basically the excess of synchronization is quite related to schizophrenia, epilepsy, and the lack of synchronization is related to autism and other brain disorders like Parkinson's. So it's very important to understand how drugs can manipulate the local dynamics of the neurons to stimulate or inhibit the synchronization process. Well, let's show the neuron model I use. It's a Hinge-Marsh-Rose model. It's a Huxley model-like. Huxley is very famous model for the neurons, Nobel Prize in 1960s. And this is a simplified form of the model. This is the membrane potential, the action potential for the neurons. The Y variable is related to fast dynamics. The Z variable is related to slow dynamics of the neurons. Phi and C is related to nonlinear functions here. And I have a lot of parameters. In general, neural models, they have a lot of parameters. Here we have A, B, C, D, R, XR, and I will just change here the input current and the B parameter. So I will study this parameter space, but the same thing I will show this parameter space can be found in other parameter space. Not all, but in others. Well, the dynamics of the Hinge-Marsh-Rose is very flexible. So you can find burst activity. So the neuron start to spike and spike for a time. And you have a quiescent period and slowly spike again. And you can see some parts of the parameter space I choose, B and Y. We can find regime of burst, regime of spikes. Spikes is just this part here, and it's continuing without this quiescent time. We can see also chaotic burst. It's a mixture of burst and spike, and you can see here it's chaotic. And you can also find another kind of burst with different frequency from the first one. Why I choose this four regime? So the model can be studied using the Lyapunov exponent. And here I will plot the minimum Lyapunov exponent as a function of the parameter space I and B. Yeah? And color here means chaos for the local dynamics, for the uncoupled dynamics, and black colors will be regular behavior. So regime 1 will be this regime, it's a burst regime. This regime 2 is a spike regime. Regime 4 is another burst regime, and the color here is the chaotic dynamic. So regime 4 and regime 3, there is a strong mixing between chaos and regular dynamics. So this is the 4 regime, and I will study here. And another point to remember is the minimum Lyapunov exponent. The minimum Lyapunov exponent gives us an idea about how stable will be the neuron trajectory, the neuron state, when you perturb this state. When you couple this neuron to other, how stable or unstable they will be. So the regime 1 is quite stable. There is a minimum Lyapunov exponent more or less minus 3 or 3.5. Regime 2, this is the spike regime, so the minimum Lyapunov exponent is around 2 or maybe 1.5. And regime 3 is the chaos regime, so you have part of them in red, so minimum Lyapunov exponent large, and this mixture here is not so large, but still higher than the black, blue here and here. Yeah. So what is important? Yeah, well, why I have computed the linear stability of the neurons, or to couple. Let's couple those neurons with those 4 regimes. I will simulate a network in all that 4 regimes. So I will add a synchronization current here, and this equation will be changed by this new current. Can be excitatory or inhibitory. In fact, more of them will be inhibitory. And I will have here the adjacence matrix, the matrix that couple all the neurons. So I will use here small word matrix. Yeah, but I have results for global and other metrics. The results I will show here is not dependent from this particular case I will use. Well, I will use what Strudek's wrote for a small word network. And basically is this. We start with a local coupled neuron. So each neuron here has coupled 2 neurons from the left side, 2 from the right side. And then what Strudek's wrote say, unplug one local connection and plug this neuron to a non-local connection. And we do this for 10% of all local connection, and we will have a small word network. If we do this unplug and plug for all these nodes, we will have a random matrix, but I will do just for 10% of them. So let's remember the 4 regime again. So this is a periodic burst. So this interval of time between bursts, they are equal. And here is a spike. It's also periodic. And the chaotic regime, the burst is not the time the burst start. The interval between 2 is not the same. Yeah. So we have all these characteristics, but I will do simulation with all neurons in regime 1, all in regime 2, if so on. So my network will not be mixed. Some neurons in regime 1, some neurons in regime 2. No, all of them will be in regime 1, another simulation, all in regime 2, and so on. Well, I need to compute, I need to measure the synchronization levels, and as Tiago told, and also other speakers told, I will use Kuramoto order parameter, but I don't have a phase in this model, so I need to build a phase, and I do this using this equation. So for the first burst, I call this is K echo 1, yeah, and here will be K echo 2, and between 2 start of bursts, I have a linear interpolation from the time the burst occurs. So the first burst starting tk and the second tk plus 1 and so on. And I can build a phasing this way and use the Kuramoto order parameter to evaluate how coherent will be the phase for all neurons. I will use 1,000 neurons in my network, so J will be from 1 to 1,000, and I have a function theta J for each neurons now coupled in a network. If all neurons start in similar time, the parameter, the Kuramoto order parameter will be almost 1. Otherwise, if the time they start to spike or to start a burst is very different, the order parameter will be 0 or almost 0, very small value. So coupled neuron will behave as a function of the coupling. Yes, they have this influence, but also depend whether the individual dynamics show chaos or not. Yeah, when the coupling between neurons is weak, the coupling induces two very distinct effects. They can produce cooperation, they can produce a collective dynamics, but they can also produce another effect that is diffusion. So if you start with a regular neuron, a small coupling for equal neurons try to synchronize those regular neurons. It's a phase locking process, quite known in physical books. But if the neurons are chaotic, so you have a threshold for start the synchronization process. So you have a gap. Regular neurons start to synchronize. After the coupling, try to synchronize. Also, the coupling causes diffusion. And the diffusion may change the local dynamics in a chaotic dynamics. So it's a two very, very distinct features for the coupling. They introduce phase locking for regular, but also introduce diffusion. So the neuron trajectories will try to see what is the most important. If the neuron start to synchronize first, we will see synchronization for small coupling. But if the diffusion start first, then also we will not see this diffusion for small coupling. So let's start to see those four regimes. Taking a look in this minimum Lyapunov exponent again. So regime 1 and regime 2, both neurons are regular, but the neurons from regime 2 has Lyapunov, they have a minimum Lyapunov exponents much bigger than this regime. So regime 1, the neurons are quite stable to perturbation. So for small coupling, the phase locking try to synchronize them, and that's what we see here. The mean order parameter goes to values 0.28, 0.9 more or less, but as the coupling go and get larger values, this diffusion process imposed by the network destroy this synchronization. After, for some very high values of the coupling, the network start to synchronize again. The regime 2, the neurons here is very sensitive to perturbation, more than regime 1, because the Lyapunov exponent is large. So you can see the diffusion starts much quicker. So you don't have this synchronization in the regime 2. And the synchronization for large values of the coupling also occurs similar, but since the neurons they are more sensitive to coupling strength, the synchronization start in a value smaller than in regime 1. Regime 3 is the chaos regime. So in the chaos, you don't have at all synchronization for small coupling. You just start diffusion of the trajectory already chaotic, individually chaotic, and after that, the synchronization occurs. If you look here, you see the linear stability of the chaotic regime is even smaller than the regime number 2. So you have the synchronization of the network start even for smaller value than regime 2. And regime 4 is this figures here. you see is very similar. The behavior is very similar to regime 1. You have synchronization for small coupling, and also you have the synchronization for large coupling that starts much earlier than here, because here you have the chaos mixed here. So you have a mixture of this behavior and this behavior in the regime 4. Well, this is just an overlook in the process of synchronization, but I would like to show here another picture. So here is the maximum Lyapunov exponent, here is the minimum Lyapunov exponent, and here in color code in the parameter space YB, as I told before, I will plot the value of R. So red colors here means synchronized networks, black or dark colors will mean unsynchronized network, and the coupling starts from very small values in A, and I will increase the value of the coupling until F. So let's see. The regime 1 for small coupling is synchronized because the neurons here they are tolerant to perturbation, so they phase lock, the network phase lock. The regime 2 is almost completely unsynchronized for small coupling, and these regimes here is these regimes here, and the fingers they are chaotic, so those black fingers inside, and regime 4 is also coupled by small coupling. If the coupling is increased, you will start to destroy the synchronization, the synchronization for small coupling, and at some value of the coupling, you will see just a small part of the parameter space B and Y will be synchronized. All network here will be unsynchronized due to diffusion. And if the coupling keep increasing, we will see another effect that we call the driving regime of the network, when the coupling is strong enough, large enough to impose a synchronization for the all network. So if you stay increasing the coupling, the red area here is increasing, is growing up, and if I use a very large coupling, we will see this figure completely red. So this figure is very, very similar to this and this one. So the only explanation for this is the stability of the local dynamics, how the local dynamics try to resist to the coupling effect. So if you have strong stability, you have coupled network even for small values of the coupling strength. And otherwise, if you are interested in this regime, they are the neurons here, they are very sensitive to perturbation, so the network start uncoupled. So it's quite important even for drugs, because almost all drugs in pharmacology, they try to change the local dynamics. The drugs, they don't try to change the coupling itself. Yeah? So it's important to understand if you are near regimes of like this one, because if you change your neuron from here to the border, the synchronization will be completely different. So just to make some conclusions about what I'm told here, there are two distinct mechanisms that can lead network to phase synchronize. The first one is strongly related to the individual characteristic of the neurons, such as its linear trajectory stability. In this case, the synchronous state of the network may occur for very low values of the coupling, depending on the local characteristic of the neurodynamics. It's almost independent of the network topology. almost independent. I have tried many topologies. The second synchronized state is induced by the coupling itself. In this case, network coupling strength promotes a synchronized global state, and we say this is the network driver synchronization. The first mechanism is certainly a function of the stability of the local dynamics, and in the second mode. But for the second regime, where we say the coupling acts like a driver over the network for higher coupling, the stability properties of the individual neuron's trajectory also play a relevant role. Because if you have very stable neurons, you need more perturbation, more coupling strength to synchronize the network. So that's all I would like to say today. It's important to remember that all the first work about synchronization, they are just trying to coupling strength to analyze the network synchronization. That's not all. We need to understand the individual dynamics also. Thank you to everybody. Thank you, Marcos.
Okay, thank you very much, Sergio, for your talk. We finally have a question from our YouTube audience. It's from Gabriela. I'm going to read it to you. So the question is the coupling of neurons in your model also based on non-neuron relations like neurotransmitters? So he asked that as far as I understood, they are, but I would like to know a bit more.
More or less, as a physicist, not a physician, we try to simplify things. Sometimes we try to simplify too much. But the coupling is just a current that the neuron receives. It's an integration of the signal of some neurons. Yeah, because these A, E, A, I, J here, some neurons are coupled because we have a adjacency matrix here, and I sum all these input signal. There is a normalization factor here. This is the coupling. So the neurons receive a sum of other neurons' input. Yeah, it's quite simplified. I'm not sure. Probably in a real biologic model, this simplification is not completely correct. In fact, because you have much more interference from the medium.
Okay. Also, I also have a question, since there are no other questions so far. I don't quite understand how you can get synchronization for very small coupling. I mean, if the coupling is 0, there should be no synchronization, right?
Yeah, that's the problem with this kind of signal, Marcos, because even when you start running the initial conditions, because these areas here, you start with random conditions, but the neurons, they are regular, and so there isn't too much possibilities for the dynamics. So they start, it's not synchronized, it's almost synchronized. So the R values is more or less something more or less about 0.7, 0.6. But that's the problem with the dynamics of the Ringe-Marsh holes.
Okay, I see. Okay.
Yeah, there isn't too much possibility to differ the neurons itself.
Okay. All right, thank you. So thank you very much, Sergio. I think we are again running out of time. So
Okay.
I'd like to move on to the next speaker. Okay, so next speaker is my friend Francisco Rodrigues. So it's very nice to have you here. Thank you very much for accepting the invitation.
Thank you.
And Francisco is also from the University of São Paulo, from the Institute of Mathematical Sciences and Computation. And today he's going to talk about prediction and inference in complex systems. So please go ahead and share your screen.
Thank you, Marcos, for the invitation. Let's share my screen. Okay. Can you see my screen?
Yes.
Okay, good. Okay, let me start, okay? Okay, thank you for the invitation. So I'm talking about how you can perform the prediction and inference in complex systems. So you know that a complex system is made of parts that are connected, which cause the phenomenon of emergence. So you have that a complex system is made of interconnected parts. So you have complex systems in social networks, in food webs, in power grids, in the Wikipedia, in climate, in the internet. So you have complex systems everywhere, okay? So the structure of complex systems can be represented by a network. So you have a complex network, and the complex network we can study in three different ways, okay? So we can study the structure of the network, the dynamics, and we can also apply networks in different areas. So the structure of the network, we are interested in describe the topology of a graph. So you have, for example, a network like this one, and then you want to describe the topology by calculating some set of measures. For example, you want to describe the density of connections, the distance between nodes. So in this way, what we do is represent the network as the adjacency matrix. In the adjacency matrix, we have the elements that are equals to 1 if you have a connection between A and J, and 0 otherwise. So following this idea, we can calculate the degree. The degree is just the number of connections we have for each node. And from the degree, for example, we can calculate different metrics. We can calculate, for example, the moments of the statistical moments of the degree distribution, the variance, the entropy. So following this idea, we can differentiate between different types of topology. Another fundamental measure is the distance. So for example, you have the distance between Mary and Peter is 1, 2, 3 connections. So this distance is 3. And following this idea, we can verify how easy is the transfer of information in a network. Another important structure is the community structure. So in this case, we have a network made of group of nodes that are densely connected to each other. Okay, so these nodes forms the communities. And also another important property of the network is the centrality. So in centrality, we have some nodes that are very important for information transmission, for example. So in this case, we have a hub, and the hub is connected to a lot of nodes, okay? But not only the hub is the most central. We can have, for example, nodes that are in the periphery of the network, but it connected to big areas. They present a high between centrality, so these are also central nodes. And centrality is important for protein interaction, for genetic networks, for the internet, and also for social network. So following this idea, we can describe the network topology by using this set of measures. So different measures have been developed for this. And the idea is to describe different properties of the network. Okay, so if you take a look only on the graph, we will not be able to extract some useful information. After describing the structure of a network, we can analyze how the structure influences dynamical process. For example, given that you have a network, how this topology of this network will influence the evolution of cooperation or evolution of some spreading dynamics. So the basic idea, we have a network. For each node, we associate a dynamical process, which is described by a differential equation like this one, okay? So following this idea, we can have, for example, synchronization, epidemic spreading, rumor spreading, cascade failures, cooperation, opinion dynamics. So we can have different dynamical process in networks. And basically the idea is to verify how the network influences the evolution of the dynamical process so that you can change the network in order to control the evolution of the dynamical process. So if you know exactly how the network is affecting the dynamical process, what you can do is change the network in order to change the dynamical process, okay? So following this idea, we can control dynamical process. For example, we can control the transmission in power grids. We can control the evolution of some brain disorders by changing the brain organization. And also we can control the epidemic spreading. So one important dynamical process is synchronization. So you have synchronization in many different systems, in fireflies, in lasers, in neurons. And a very paradigmatic model that use to study synchronization is the Kuramoto model. In the Kuramoto model, we have the evolution of the phase. It depends on natural frequency of each oscillator, but also depends on the coupling between this oscillator and the other neighbors. Okay, so following this idea, if you increase the coupling, we'll have the emergence of synchronization, and the emergence of synchronization depends on the network structure. So, for example, the critical coupling depends on the average degree and second moment of the average degree of the degree distribution. Okay, so it's related to variance. There are many variations of the Kuramoto model, but the Kuramoto model is very important to understand synchronization in network. But there are many other dynamical processes. For example, you have spreading dynamics. In this case, you have the spreading of virus, bacteria, computer virus, and some other types of information. And for example, here you have the propagation of the bubonic plague in the 4th century. So you can see here, for example, the epidemics started in Turkey and the south of Italy in around 1347. And the epidemics took about 4 years to reach Sweden and Finland, for example. Okay, so it took 4 years to go from the south of Europe to go to the north. Okay, just for comparison, here you have the epidemics in 2009 or flu pandemics. The epidemics started in Mexico, and after just 3 months, the epidemics reached all the continents. Okay, so you can see that the spreading is very fast today compared with the Middle Age. Okay, and this happens because the network structure influences the evolution of the epidemics. So, for example, today I can take a flight from São Paulo and go to China in just 1 day. And in the Middle Age, people usually stay in a small village, and these villages were not connected, so the transmission of the disease was very, very slow. Okay, to study epidemic process, we have 2 different approaches. We have theoretical models in which you can develop some equations that will describe the evolution of the infectious agent, but also you can have some data-driven models in which you have data from real-world epidemics, and you can use this data to develop some models based on statistics, machine learning, and some other tools. Okay, so basically to understand epidemics, we have 3 states. We have the susceptible, infected, and recovered. So someone is susceptible, you'll be infected and can be susceptible again if someone will recover, but is not immune to the disease. But for some diseases, like measles, for example, we have that someone can become immune, so you have this recovered state, and this person will not be infected again. Okay, so you can change this idea and develop some different models, but they are more or less similar. And the models were developed initially based on fully connected graphs. Okay, so we have fully connected graph, but in real world we have networks. So what you can do is adapt the models to complex networks. So following this idea, we have different approaches, but the most common one is the degree-based mean field. Following the degree-based mean field, we can solve this set of equations and find that the critical rate from the propagation of the disease depends on the network structure, depending on the average degree, and also the second moment of the degree distribution. Okay, so we can see that synchronization and epidemic spreading depend on the network structure. And also this happens for rumor spreading. So for rumor spreading, we also can verify the same phase transition. For example, here in this recent paper, we verified that this phase transition occurs for very small coupling. Okay, and following this idea, you can use mean field, the Markov chain, quantitative mean field. You can have different ways to study epidemic spreading in networks. But all these studies show that we have a very strong dependency between the network structure and dynamical process. So the network structure plays a fundamental role on epidemic spreading. Okay, and at the end here we have some different applications. So we have applications in physics, biology, medicine, and the idea is to use concepts from complex networks and apply in different areas. Okay, so if you know that the structure of the network influences the dynamical process, one important question is how we can predict and infer this influence in complex systems. Okay, so by using different dynamical process, we can study how we can predict and perform the inference, okay? So this is the basic question we wanted to solve. And we have two different tools here, okay? Two different tasks. The first one is the inference. The inference, what you want to do is to explain the data we'll have. So for example, you have a network, we have synchronization. You want to understand which properties of the network is influencing the dynamical process, okay? In the case of prediction, what you want to do is, based on the data you have, you want to predict new data, okay? Given that I have a network, we will extract some features from the network, put in a black box, and then predict the dynamical process. This is the idea. So in the first case, you want to understand. In the second case, you want to predict. And also you can perform this prediction and the inference in the global level, so in this large scale network, or in the local level, which is the level of the node. So our hypothesis, given a dynamical process, we'll infer some function that is applied to network topology, and then we'll be able to predict the dynamical variables, okay? So for the case of the global level, what you have to do is to change the network structure as much as possible to give some information to the model, to a statistical model. So you have different models to generate networks. And also you need a set of variables to describe the network structure. So basically you have different types of topology, different measures. We'll combine this in a kind of model like this one. And by using this model, for example, this is the average, this is the network measures, okay? So by inferring this model, by using Bayesian regression, we can verify, for example, in this case, that the shortest path is the most important network property related to synchronization. So for example, if you wanted to change, if you wanted to improve the synchronization, what you have to do is decrease the distance between the nodes. So this is negative, so it indicates that as you increase the distance, we decrease the synchronization, okay? So following the same idea, we can apply for epidemics. So in this case, we use a beta regression model. So by using this idea, again, we can infer the importance of each network measures. And for epidemic spreading and rumor spreading, we verify that the average search information is the most important network property. The average search information basically is the number of questions like yes or no we need to perform to go to one point to another one. So if you wanted to navigate in the network, the average number of questions we needed to go from one point to another one, this is the average search information, so our result makes sense. So here's the prediction, here is the observed values, here's the predicted values. You can see a very good correlation. So you can see that you can predict the epidemic spreading and rumor spreading based on network structure. In the case of local level, so you wanted to predict, for example, the node dynamics from the network structure. And here we have that the nodes are not independent. So for example, if you remove this red node, we will stop the connection between all these different nodes. And you wanted to predict the epidemic. So for example, given that one node is infected, I wanted to predict the size of the outbreak. So for example, given that I am infected, the epidemics start with me, how many people will be infected? So this is basically the idea, to try to predict the average outbreak size. In the case of synchronization, given that we have one oscillator with some properties, we wanted to predict if this oscillator will synchronize. Okay, this is the idea. So in this case, we have a regression model. In this case, we have a classification model. Okay, so this is basically the framework. So you have a network. We extract some set of nodes. By extracting some set of nodes, we will extract some information about the structure and dynamics. We will train a learning model. This model will be applied to the remaining of the nodes, and then you can try to predict the network evolution, okay? So our data is, from the network, we extract different features from each node, and our output, so our target variable is the dynamic variable, okay? So in this case of epidemic spreading, you want to predict the size of the outbreak, and synchronization, we have two-class classification. So we want you to predict if the oscillator will be synchronized or will not be synchronized. For the learning models, we use a random forest. A random forest is just a collection of decision trees. So you have different decision trees. So we will have our data. We perform some kind of bagging in which we extract some samples. From these samples, we construct the decision trees. And by using the majority voting, we can decide about the classification and the regression. And also you use deep neural networks to perform the classification and the regression. So when you use this idea, so you have the data, you have the prediction, and you can see a good correlation. So you can see that by using this idea, we can predict the evolution of dynamical process by using network properties. So for example, if you wanted to predict the outbreak size or if oscillator will be synchronized or not, we can use the network properties. But also, if you use the random forest algorithm, we can try to predict the influence of each network property on the dynamic variable. For example, for epidemic spreading, we can see that the key core is the most important one. So for example, if you have a node with a high key core, this node will be the main spreaders. So in this case, we can see that this node will be the most influential spreaders. So this is a very important problem in complex networks. So this idea can be used to infer this importance. Okay, so you know that in your society, we have some people are more important than other ones. So if you use this idea, we can try to infer the importance by using machine learning. Okay, in the case of synchronization, we can see here is the prediction. We can see that the Hawk curve is about 0.8 is a good prediction. So you can see that if you change the coupling, we can also predict it. Of course, that you have a region that the prediction is more accurate. And also we can try to infer the importance of each network property for synchronization. So when you change the coupling, we can see that for low coupling, the key core is the most important one. But when you increase the coupling, the between centrality starts to become the most important one. So you can see that in this case, the key core is a more local measure. We will measure the local organization of a node, while the between centrality will quantify the importance in a more global level. Okay. So basically what you conclude is that if you have some information about the network structure and dynamics, we can try to infer the dynamical variables from the network structure. Okay. But also we can use this idea about inference in prediction in case that you have some data. Okay. So it's a data-driven prediction and inference. In the case of the brain, for example, what you can do is extract data from fMRI. So in this case, what you have is images from the brain. So you have some people that present, for example, schizophrenia and people that are healthy. And then from these images from the brain, we will construct a network, a cortical network. By using descriptors for this network measures, we will extract these descriptors. And then we apply some learning method, for example, random forest or some deep neural network. And then we will be able to classify some subject as presenting schizophrenia or if someone does not present. Okay, so you can perform the automatic diagnosis. Okay, so this is basically the idea. So you use the data from shield onset of schizophrenia. So it's a schizophrenia that occur in young people. We have our data set is 20 people that are healthy and almost the same number for people presenting schizophrenia. And we extract 54 measures, so for each node. And then we perform the classification. You can see that just 4 measures are important. So for example, we verified that the brain of people presenting schizophrenia and people that are healthy differs in terms of modularity, so in terms of the modules, we have network, and also in terms of centrality. We also applied this for Alzheimer's disease, and also we verified that we can predict if someone have Alzheimer's based on this idea. So you have that the brain of people presenting Alzheimer's is completely different from someone who is healthy. And also we will apply this idea to autism. So in the case of autism, we also have data for about 500 people. And when you extract several network properties, but here we have important point is how to construct the connectivity metrics. For example, you use different approaches like Pearson correlation, Granger causality, and some other measures of causal inference. And we verify that following this idea, we can have a very accurate prediction of this mental disorder. Okay, so following this idea, for example, in near future, we'll be able to just put the electrodes in the brain of some kid, for example, and try to verify if this child will present autism or not. Okay, and also you will perform one experiment with a ayahuasca experiment. So ayahuasca is a kind of drug that people use mainly in the Amazon. And following this idea, we verify that when people take this kind of drug, the brain will change his topology. Okay, so the function of the brain will change, and you can capture this change by using this same idea. So you have the people before, okay, so you have the signals from the brain. People take the drug, and then we record after, and verify that the brain will change. Okay, so you verify that you can classify very well how this brain is changing. And also, when we verify which properties we are changing, we verify that the closeness centrality and the assortativity are very important ones. And also, closeness centrality are related to Alzheimer's disease. So this implies that in some way the brain is changing the centrality and the assortativity. And if this is related to Alzheimer's, it implies that maybe this drug can be used to treat Alzheimer's. Okay, so this is just a starting work, but we hope that this will help to understand how we can change the brain in order to avoid some or treat some diseases. Okay, so these ayahuasca experiments provide us some clues that we can follow to try to develop new drugs. Okay, and also we have epidemic spreading. So in this epidemic spreading, we use causal inference. In the case of all causal inference, we have that correlation does not imply causation. Here you have, for example, the case of polio. In the US, you have here the consumption of ice cream. Here you have the number of new cases of polio. And you verify a very good correlation, but they are not causing each other. Who is causing is the summer. Okay, so is the summer people will move to the beach and will contact each other, and this will increase the number of cases. Okay, so following this idea, we wanted to connect epidemiology with causal machine learning. Okay, so the idea is we have data from cities, for example, or some different places, and then we wanted to verify how one city, for example, is causing the number of cases in another cities. Okay, so this in this case we will construct a network. So what you do is use not only data from different cities, but data from different sources. For example, you combine data from dengue with climate, and then we will try to improve the models that try to predict the number of cases of dengue by using this idea. So you verify that if you combine climate variables with the number of cases, we can develop a more accurate model. And here we have the prediction for São Paulo, Sorocaba, and Belém. And here in black, you have the number of cases. And here we'll have the prediction. So you can see that if you combine these climate variables with the number of cases of dengue, we can improve the prediction. So you can have a very good prediction and improve the models. Okay. And also you have the idea by using what is called transfer learning. For example, for some diseases, we don't have much data, like Zika and COVID, for example. But what you can do is try to use one data to try to predict another disease. For example, you have data from influenza, and use this data to try to predict COVID, and data from dengue to try to predict Zika. Okay. So following this idea, we estimate for different cities in Brazil, and we verify that we can improve the prediction. Okay, so you can, for example, verify. Oh, it's not, the plot is not here, but okay. We verify that we can improve the prediction, and also we can use this idea to verify, for example, the number of cases that it was expected during the the pandemics. Okay, for example, during the pandemics, people avoided to go to hospitals, and we wanted to verify if this influenced the number of cases of dengue. Okay, so we verified yes. Okay, so climate dynamics is the same. We wanted to predict the climate by using causal inference. So, for example, in this work, we predicted that the El Niño plays a fundamental role in the dry season in Ethiopia. So, in conclusion, we can see that machine learning statistics are very important tools to understand complex systems, and we believe that these new tools will help us to improve how to simulate, how to understand, how to predict, how to forecast, and how to infer properties of complex systems. Okay, thank you. This is my contact. So if you have any questions, I will be happy to answer. Okay, thank you.
Okay, Francisco, thank you very much for the talk. Very, very interesting. We have a question here from Nathan Berkovitz. I'm going to read it to you. So the question is, naively, the dynamics of disease spreading networks is different from rumor spreading networks, since people try to avoid diseases, whereas people try to hear the news rumor. So why are the models similar?
Yeah, the model is similar in the following. For example, when you have the epidemic spreading, for example, I am infected. So I am recovered by myself. I don't need any help. Okay, so I recovered from the disease. When I am spreading some rumor, I spread. But when I meet someone who also knows the rumor, I will stop the spreading, because it's like to tell a joke. Okay, if I tell a joke that someone knows the joke, I will stop the spreading. Okay, but this is true. Okay, this is true because people usually try to avoid the epidemics, but in the case of rumor, people try to spread if they are very interested in the rumor. But we verified that the network navigation is related to how easy the information will be transferred in a network. Okay, so we verified this is the most important property because it's expected, I think, because we expect that if it's easy to navigate in a network, it's easy to propagate information. And rumor epidemics are two kinds of information.
Okay, thank you. I also have a question about this brain diseases. So when I hear from people who make these measurements, so they put all these electrodes in the brain, they measure some type of correlations, and then they extract a network from these measurements. So what they tell me is that every time they do the measurement in the same person, they get a different network, that things fluctuate a lot. So what's your take on that?
It's very complicated. For example, for fMRI is more accurate because you put someone in the scanner and it's easier to but the problem is it's expensive, and it's expected more almost 1 hour to perform the recording. Okay, but when you use the EEG is very cheap. Okay, it's very easy to extract, but of course that will have this problem. So what you have to do is perform several times. Okay, this measure by for example, you ask someone to perform some task, like for example, move the hand, and then you extract some kind of average measure of several recordings. But this is complicated. But that's the point. For example, this is cheap. Okay, so you have a lot of noise, but it's easier to collect the data. Okay, so this is what we're trying to do, is use this kind of data because it's easier. But of course, these problems, we have a lot of problems.
But you can be sure that this when you have a person with Alzheimer's or healthy people, the networks are going to be different in some way.
This is what we verified here. You can see, for example, this is the Hawk curve. We can see is about 92% of correct classification. So you can see that although you have this oscillation between different measures, we can see that some patterns are well defined. Okay, so you have very strong difference between them. For example, for the deficit of attention, it's not so easy to perform this diagnosis because the difference is very subtle. For some diseases, it's easy. Alzheimer and schizophrenia is the easiest one, because the difference in the brain are very well defined. But for ones, it's not so easy.
Okay, thank you. Any other questions? We have 1 or 2 minutes. Okay, so I guess this is it. So I'd like to thank you all the speakers very much for the talks. I think it was a very interesting session, and I think we can end the session now. Is there anything else I should do here? Okay, so I think I declare this session ended. Thank you very much again. Hope to see you all soon. So you have a great evening wherever you are.
Okay, bye.
Thank you. Bye-bye.
Okay, thank you. No, it's just thanking the speakers. Okay, it's not a question.